great attendance coming. So should be really good.
Yeah, I hope we get a high percentage of the people.
All right, good morning, everyone. My name is Isaac Montoya, and I'm the Director of Marketing here at Upsite Technologies. First of all, I'd like to thank you all for joining us here today. We are always excited to talk about airflow management, so we are happy to be here with you today to talk about row airflow management specifically. I'll be joined here shortly by Rob Hudeman, Senior Vice President of Operations at Critical Environments Group, as well as Lars Strong, Senior Engineer and Company Science Officer with Upsite Technologies. But before I pass it off to them, I want to go over a couple housekeeping items. So everyone will be muted on this call, but we encourage you to ask questions, and you could do so using the Q&A module in the Zoom dashboard, either located at the top or bottom of your screen. Also, if you have any technical difficulties, please feel free to send me a message using the chat module, and we will try to get that resolved for you as quickly as possible. Now, real quickly, I also wanted to say I hope that everyone is staying safe and healthy during this unprecedented time. This pandemic has definitely affected all of us around the world. And I just hope that all of you and your families and colleagues and communities are staying safe and healthy during this time, and hopefully we can all get through this very quickly. Okay, so as I mentioned, I'll be joined here today by Rob Huddeman, Senior Vice President of Operations at CEG. Rob has over 30 years of industry experience in data center infrastructure management, with a lot of that being focused on power, space, and storage, cooling, and overall data center operational best practices. We also have Lars Strom, Senior Engineer and Company Science Officer here at Upsite. Lars is a recognized thought leader and expert in the industry and has spoken at many industry events on topics regarding airflow management, cooling optimization, and many others. So I think it goes without saying that between Rob and Lars, they bring both a wealth of experience and knowledge in this arena of airflow management and cooling optimization best practices. So we're definitely happy to have them on the call today, and hopefully everyone here, can learn quite a bit. Again, we encourage questions during this call, so please, please ask those through the Q&A module, and we'll try to get to as many as we can at the end in the Q&A portion of this presentation. Thanks. And without further ado, I'm going to pass this off to Lars to get this thing started.
Thank you very much, Isaac. Well, I want to personally thank everyone for their time. I'm very excited that you're joining us today. Here's the agenda that we're going over. We're going to discuss the 4 R's of airflow management, a concept that Upsite developed. We're going to talk about some of the lesser known row airflow management best practices, get into data center containment best practices as they relate to row level containment. We'll talk about the science of data center containment and look at the differences between modular containment and legacy containment, some considerations around cost and savings. And we're going to look at the cooling capacity and IT load and how to match those, the process of optimization. And we'll talk a little bit about bypass airflow and give you a concept called the 4 delta T's that should help you when you approach these processes of optimization in your room. And hopefully we'll be able to get to a lot of your questions towards the end. So the 4 R's of airflow management is a concept that Upsite developed to help data center managers focus their efforts and recognize that there's really 3 areas of airflow management improvements that can be made: at the rack level, at the row level, and at the raised floor level. And after improvements are made at any one of those different areas, it's necessary to check in and make adjustments at the room level with cooling unit set points and controls to be able to realize the benefits of those improvements. And we're going to talk about this concept a little bit more as we go through the presentation. I want to get started just with a reminder of the importance of rack airflow management. This presentation is the second in a 4-part series, and the first series was focused on rack airflow management. So just to revisit that for a moment, it's very important to seal the open space across the vertical plane of IT equipment intakes, and that's some of those areas are related to row airflow management. We'll talk about those in this presentation. But everything within the cabinet, the blanking panels between open spaces and between IT equipment, and sealing the space between the rails and the side of the cabinet are very important for both blocking exhaust recirculation and potentially blocking the loss of bypass airflow, conditioned air flowing through a cabinet where it shouldn't. So that presentation was covered, and those areas were addressed in the last webinar. The third part in this 4-part series will be focused on room level containment best practices. And then the 4th one, coming in June, will be focused on the raised floor best practices. All right, so Rob, you ready to take it away? And Rob, you might be on mute.
Try it again.
There we go.
Okay, thank you, Lars. So when we talk about row airflow management, we're referring to improvements in separating cold supply air from hot exhaust air at the row or aisle level. Row level improvements are typically addressed after you've taken care of the rack level and floor level improvements. And row level improvements usually always involve sealing off the hot or cold aisle ends with some type of door and dealing with the area above the row or aisle by capping the cold aisle or channeling the hot air above and out of the hot aisle. So these 4 bullets represent the key best practices for row or aisle level airflow management. We'll get into much greater detail on each of these on some of the subsequent slides, but I wanted to do a quick overview right now. So the first thing is blocking off open spaces under the racks. So cabinets are often delivered with casters and levelers to aid with initial deployment. So if your cabinets have casters and levelers, then by default, you'll end up with a gap between the floor and the bottom of the rack. And blocking this gap is what we're referring to here. The second is sealing open spaces in the cabinet rows. So depending on site conditions, some layouts will end up with gaps between the racks due to support structures, other types of barriers in the room, or intentional space that's been left there for a future roll-in rack. Installing aisle end doors. So this prevents the wraparound mixing that will occur at the aisle ends if doors are not used. So doors are very important, and they're available in many designs from a variety of manufacturers, and we'll get into greater detail about doors on some of the subsequent slides. And lastly, the top of rack containment. So hot aisle containment typically features an above rack barrier around the perimeter of the hot aisle and typically extends upwards from the racks to the top of the ceiling, or vice versa from the ceiling down to the top of the racks. And cold aisle containment could involve a roof or a capped aisle or even a partially capped aisle that spans across the cold aisle. And again, more to come on both of these as we get into the presentation.
All right, thank you very much, Rob. So it would be nice if airflow management was visible, if you could see the air moving around in a data center. And it's not, and that creates a lot of challenges. And a lot of people think they're doing a better job than they actually are, and that creates opportunity. The good news to that is that there's opportunity for both reducing operating costs and improving the conditions in the room and recovering some stranded capacity. So this image shows, even though that hot and cold aisle layouts have been implemented in a room, there's the potential for a lot of poor airflow management. You can see that in this image, there's a lot of hot air circulating over the tops of the cabinets. Hot exhaust air can circulate around the ends of the cabinets. As Rob mentioned, aisle end doors are necessary at the row level to prevent that from happening. And conditioned air is being lost out of the cable openings or misplaced perforated tiles. We're going to be covering that in the raised floor presentation. So there's a lot of room for improvement, and row airflow management will help you get to an ideal scenario. We see now in this image that everything is as it should be. There is no exhaust recirculation. The amount of conditioned air being delivered to the cold aisle equals the amount of conditioned air required by the IT equipment. So there's no waste of bypass airflow, no waste of that expensive conditioned air. And we'll talk more about that concept, show you some images of how that works later on. So to get there, let's start talking about these actual practices. As Rob mentioned, many cabinets are delivered with casters or leveling feet, and this creates a space underneath the cabinets. Most people tend to think of the hottest location in a cabinet being at the top of the cabinet, but many times in computer rooms, I've found the highest intake temperatures located at the very bottom of the cabinet. Might be the very bottom 1 or 2 U in the cabinet. And this is the result of hot exhaust air circulating underneath the cabinet and flowing into the IT equipment intakes. Now, the problem cannot be solved in many cases by adding more conditioned air or colder conditioned air. It's simply that the exhaust air flowing under the cabinets is displacing the conditioned air that's there and available. So when these openings are sealed, you can see that the intake temperatures have dropped substantially. And these images are the result of detailed CFD analysis of a computer room. And there's a direct relationship between the evenness of intake temperatures and the efficiency of the room. The goal is always to get intake temperatures into all of the IT equipment, every single U, as even as possible. And that will directly relate to how efficient the room can become. So let's take a look at a couple of images of what these actually look like. You know, on the left is obviously a space you've all seen, an open space underneath the cabinet, and sometimes these can be even smaller, you know, just an inch or smaller, and still that can allow a substantial opening for exhaust air to recirculate under the cabinet. So there's a number of different products available that attach both with adhesives and magnets to block this open space and prevent that recirculation of exhaust air. The next example is a little more common, and people are aware of the problems of this one, of course, which is openings in the rows of cabinets. And this CFD analysis of conditions B4 with the area open shows the hot exhaust air circulating through those spaces and causing elevated temperatures along the edges of the cabinets. Not the entire server. The server, if there's inlets across the full face of the server, over farthest from the gap is getting nice cold air, but right next to the gap is getting very hot air. So it's important to consider intake temperatures at a really granular level, because sometimes monitoring or even sensors within the equipment can miss these high intake temperatures in very isolated locations. So once this gap is sealed, the opening is blocked, of course, and now the exhaust air cannot flow through that space, and the conditioned air that's available in the cold aisle can now make it to the inlets of the IT equipment. And it's important to point out that in both the CFD models for the under rack openings and this in-row opening, that there was no change in the amount of conditioned air supplied to the aisle or the temperature of the conditioned air before and after. These before and after images are purely the result of just blocking an opening.
Thanks, Lars. So here's a couple real world examples of installs where you see this type of application. So kind of on the left and in the middle is a kind of a before and after, right? This is using a rigid vertical kind of blanking panel to accommodate the situation. This is in a co-location. It's in a caged environment. You can see a very large building support column there between the end of a rack. This is a new deployment, so there hasn't been any hardware put in. It's actually the perfect time to do containment projects. But there's 48 inches and plus a little bit between the edge of that rack and the cage, right? And so you got the column there. You got kind of a 24-inch wide space and then the column. So what the customer asked us to do, they required vertical rigid panels, and instead of building one that spans 48 inches wide and the height of the cabinet, there's two of them side by side that are kind of attached to the adjacent panel. And the first one can be removed because this is that roll-in consideration I mentioned earlier, where they would like to in the future be able to roll another cabinet in there, so they can just take this panel, the left panel, out, put the cabinet in, and reattach the right panel to the end of the cabinet. On the right, this is an Upsite product. It's called a rack gap panel. It's a great product in that it can actually span these gaps. It can span anything from like kind of less than a foot up to almost 5 feet in width. So it's a universal product. It's used for the same application. It's an opaque product, so you know you've got options there between doing something kind of rigid and designed specifically for a particular cabinet height and an aisle width, or there's something that's a lot more flexible and repurposable in these rack gap panels. So this is the unique scenario, right? So sealing spaces at the ends of the cabinet rows. We're not yet quite yet talking about doors. So this scenario is more commonly found in retrofit applications where containment perhaps was an afterthought, right? So because most vendors' door designs require that the aisle end cabinets be in alignment or on the same plane for the doors to attach and install properly, even the slightest offset can make the installation a little bit more tricky and will require some means of dealing with and sealing the space. So depending on how subtle, like a few inches, or dramatic, like maybe a whole tile or more, that this offset might be, there are a number of ways to accommodate the scenario. So if structural rigidity of the door needs to be considered, then added bracing may need to be added in addition to just sealing the gap. So what you got going on here in these pictures, kind of in the bottom left in the little inset. So this is another co-location environment. It's a wide aisle, right? You've got a cabinet on the left. You've got a 48-inch wide dual swing doors at the 48-inch width, and then you've got probably another foot to 2 feet of open aisle. And then this thing returns back. You can't see the building column, but it's another one of those big white columns you saw in the previous slide. So we designed a steel enclosure to span the rest of the aisle and return back to the column. And then inside in the insert where you got the 90-degree angle, there's a brace in there so that when these doors close, it doesn't wobble or shake, or just adds into the structural integrity. In the middle there, the larger picture in the middle, so Upsite's got a unique way of addressing this situation as well. So this is called an adjustable mounting post. So this is a rigid metal post that's got a big steel plate that you can mount to the floor, and you can position this post to align the cabinet on the other side of the aisle, or whatever piece of equipment might be. So now you've just created that common plane or alignment that you need to properly attach the doors and make them work. On the right, the last thing is, again, this particular client, again, wanted a rigid panel that you could kind of see through to do the same kind of thing. You can kind of see the doors, and then we return back to cover up what looks like, maybe 27, 28-inch offset there. So there's a variety of ways of accommodating this situation, and just be aware that it can be dealt with, but it's something you need to pay consideration to.
Nice. Thank you, Rob. So as we move from sealing smaller openings to larger and larger openings, let's start talking about doors. What everyone thinks of when they think of row containment. Doors are particularly important because cabinets at the ends of rows are really vulnerable to that exhaust air recirculating around the end of the row and causing elevated temperatures for the equipment in the cabinets at the end of the row. And doors are hugely beneficial whether or not a roof is installed. So as I like to say to people, if you have a limited budget, the first thing to do is buy blanking panels, and the next thing to do is buy doors. And then after that, think about a roof or baffles on top of the cabinets, because doors alone create a lot of benefits. So we'll take a look at a couple of different options for doors. We see on the image on the left, we've got a hot aisle and then a cold aisle. On the left, on the hot aisle, are Upsite bidirectional doors, and these are appropriate for 48-inch wide aisles and come in a variety of heights to match the height of the cabinets. And these attach magnetically. They're completely toolless. Take them out of the box, put them on the cabinets, and turn a couple of knobs, and the magnets engage, and these doors are held in place. And then you can walk through them. They swing in, they swing out. On the right, we see an example of a Upsite sliding door and a transom sitting on top of that to match the height of some taller cabinets. The sliding doors are also completely toolless, and it can be installed with a little bit of experience in approximately 3 minutes. It literally takes longer to take these products out of the packaging than it does to install them on an aisle. which makes them a very flexible solution. It enables a row to be contained, doors to go up on a row before the row is built out fully. Say a row is planned for 15 cabinets on each side, and only 5 are in place. Well, you can put up a door and contain the 5 cabinets on each side. And then when it's time to add more cabinets to the row, take the doors off and add the cabinets, put them back on. Just takes a few minutes. The baffles that are sitting on top of the cabinets, we'll talk about those in a few minutes.
Thanks, Lars. So I'm going to talk a little bit about some of the legacy, or what I'll refer to as mechanically attached examples. So there's a variety of doors on the market from a variety of manufacturers, right? And they all kind of boil down really into 2 different types. There's swing doors that, you know, you and I are most familiar with in our homes and businesses. They're hinged, right? So there can be either a single swing door like you see on the left. You know, these are sometimes more custom sized for specific gaps. If you look at this one, right, it's going between a column and a rack, but it may even be just a share over, or 24 inches wide. So that was a custom door that was made. People need to get in and out of that space. You see double swing doors in the middle, and then there's sliding doors. Sliding doors are very common, and they can come in single or double wide flavors as well. The single sliding doors, like you see in the picture, they're designed to either slide to the right to open or to the left to open. So this one would obviously slide to the left to open. This one also shows one of those return panels for an offset aisle. But the double sliding doors, very popular. They're made to accommodate a variety of different cabinet heights and widths of the doors, or widths of the aisles. And the doors oftentimes come with a stay open feature so that you don't have to hold them open when you open them, and then either a slight tug or a quick push on the door, depending on which manufacturers you're using, they'll close automatically and gracefully shut so they don't slam into one another.
Nice. So now that we've got doors on the end of the aisles, let's start looking at what we do above the row for containment. Typically, installing containment above the cabinets is done for higher density environments, but it's also potentially very important for other layouts in the room where there may be a low ceiling, and when the cooling units may be on opposing walls, causing the exhaust air from a hot aisle to flow over the top of a cold aisle to get back to the cooling units. They're always going to provide some improvement and enable the further reduction of fan speeds and potentially raising cooling unit set points to further optimize the room. In cold aisles, they look like baffles or a full roof. And we're going to show you some examples of those here.
All right, thanks, Lars. So I'll talk about the one on the right. So this is your kind of capped aisle in a cold aisle containment solution. So you're looking at a long aisle here. It's 20 cabinets on each side. They're wide cabinets. They're 32 inches wide each. The real kind of nice feature for capping an aisle is cabinets that are the same height throughout the aisle on both sides. And if you don't have that, and if you've got that kind of skyline profile, there are ways, easy ways to accommodate and end up with the same result. But nonetheless, the capped aisle, these are panels. Think of a picture frame. So you got an aluminum frame with an insert there with some special material that shrinks. It doesn't melt. It kind of deforms and kind of falls out of the frame when it reaches about 135 degrees. And that's before the temperature of a sprinkler head might go off above it. So from a fire suppression standpoint, this works well in most all environments and is supported with your local jurisdiction, because these panels or the inserts will flutter out of the frames before the sprinkler system goes off. And we're talking like way less than a pound each. These are like leaves falling off the tree in the fall. So you have, you buy these things at different widths to span the aisle. This is a 48-inch aisle. These things either rest on or mount on the cabinets across the aisle from one another. So that's an example of a capped or fully enclosed roof for cold aisle containment.
Thank you, Rob. And on the right here, we see examples of the Upsite aisle lock rack top baffles, and these angled baffles are intended for cold aisles. The angle is fixed, it doesn't move, it's not adjustable, and it's not tied to the fire suppression system. The opening is what allows this to be approved by fire marshals. Leaving it partially open prevents it from obstructing gaseous fire suppression, can obviously get in. And to date, we're not aware of any fire marshals objecting to the baffles blocking the sprinkler spread, as long as the requirement of 18 inches from the top of the baffle to any sprinkler head is maintained. These have been accepted by local fire marshals. The baffles are modular in that there's one baffle for each cabinet, and they are purchased in widths that match the width of the cabinet. And they attach magnetically, completely toollessly. You can see at the back of each baffle, those silver portions, those silver elements are a cup magnet. And so these come out of the box and you tilt them into place and the magnets attach and they're there. One of the great benefits of these is that they are removable. So if there's cable trays or a need to access the tops of the cabinets, these can easily be removed and then replaced. And you may be wondering, well, how does an open top containment work? I'll cover that in just a moment as I talk about some of the science of airflow management.
Okay, thanks, Lars. So we're going to move to some of the similar examples, but just for hot aisle containment this time. So you heard me earlier talk about hot aisle containment is building a vertical perimeter around the hot aisle from the tops of the racks to a ceiling. Hot aisle containment most times is used in a scenario where you've got an overhead return plenum above a drop ceiling. That's the case in the photo you see in the top left there. And, you know, there's going to be perforated kind of register tiles in the ceiling instead of the solid tiles that you're typically familiar with and you see here. So the hot air is going to be filling the hot aisle and hot air rises. So it's going to rise up and be drawn back to the intake of the perimeter air conditioning units in that room. And the key is there that they are also ducted directly to the overhead plenum, like you see in the photo on the bottom, right? So that's a black ductwork sitting on top of one of the new Vertiv AC units that's also the similar color. You can see that there's a hinged door there so you can get in and change filters, but that's a key component to making all of this work. Everything's ducted to an overhead ceiling return. What you see in the top right, this is a rigid hot aisle containment design. It's using rigid panels to make that perimeter from the top of the rack to the ceiling. There's also a play here for flexible hot aisle containment, and I'm talking about kind of using curtains, the flexible polycarbonate wall material that can be used. People usually refer to curtains like meat lockers, but there's definitely a play for them in hot aisle containment, specifically when you have varying elevations of power and cable management. So you see ladder rack and then a yellow fiber tray here. They're running parallel to these rows, but oftentimes you have things cutting across the rows. So it's tricky, right? You've got to navigate around different widths, different heights, different elevations. And it's easier to trim some curtain material to kind of navigate around those overhead obstructions and still have a good seal for your hot aisle containment. So there is a play for curtains there. So the hot aisle containment can be rigid or flexible. And I would just add that if you don't have a ceiling return plenum, but you do have a high ceiling in the room, so hot aisle containment could still be an option for you in that scenario, in which case you would Raise the top of the hot aisle, off the racks, kind of all the way up to where the jurisdiction says you have to remain X amount of inches, usually 18 from a sprinkler head, and stop it there. And you do the same for the air conditioning unit. You would raise that intake up. You just wouldn't be coupling it to a drop ceiling. You would raise it up, and that increases the delta T. You're going to be returning a lot warmer air to the air conditioning unit. And when Lars talks about the science and the delta T's later on, you'll understand why that's important.
I appreciate that distinction, Rob. That's a really important point to make, that there's a lot of misconceptions in the industry about airflow science and cooling optimization. And that's a very very nice example of how a creative solution can really improve the efficiency. On the right here, we see the Upsite Aisle Lock rack top baffles in a vertical configuration. So there's two different SKUs. One is angled, as I showed you for the cold aisle, and the other SKU is vertical, generally used for a hot aisle. But these can also be used for a cold aisle when there is overhead delivery, ducted supply onto, say, a slab environment, and you just need to create a higher rim for the bathtub on the cold aisle. But generally, the vertical baffles are used on a hot aisle, and they block the airflow from flowing right over the hot exhaust air from flowing right over the top of the cabinet into the cold aisle. Once you get it moving in the right direction, and if the ceiling plenum is being used for a return, and there are the openings, the registers, the return air registers in that drop ceiling are appropriately placed, then this partial hot aisle containment solution can easily get you 80–90% of the benefits of what a fully enclosed hot aisle containment solution could get you. These baffles are also modular in that there's one per cabinet, and they're sized to match the width of the cabinets. So let's move into a little bit of the science of containment and show you some schematics of the airflow paths. Obviously, with legacy hot aisle containment, we're fully containing the hot air, ducting it to a ceiling plenum, and that is returning to the cooling units that have also been ducted to that ceiling plenum. So we're forcing this flow path through the room. I'll step back and answer one of the questions that's already been asked, which is what's better, hot aisle containment or cold aisle containment? And studies, both theoretical CFD analysis and in the field studies, have proven that hot and cold aisle containment, if done well, are equally efficient. And I emphasize that if, because it's a potentially big if. Cold aisle containment is much more common. I'll explain that in just a moment. But the downside of, well, I'll talk about the advantages of hot aisle containment, which is, in this example, we're looking at hot aisle containment. And so if you're fully containing the hot air, then the rest of the room becomes cold. And the placement of supply tiles is not as critical. The air is free to flow around in the room and make its way to where it's needed. So the room feels cool. The airflow is managed a little easier. Any leakage in the floor of conditioned air through the raised floor, as long as it's not under a cabinet, goes into the general space for cooling. And so hot aisle containment tends to be more efficient because it tends to be done more effectively. When we look at the modular version of hot aisle containment, we don't have a full duct, a full chimney to the ceiling plenum, but the benefits can be very close to the same. The amount of air being delivered to the IT equipment is crucial in the process of optimization. That is, balancing the amount of conditioned air flowing through all the cooling units as closely as possible to the amount of air flowing through the IT equipment. And when there's excess conditioned air flowing through the cooling units and through the room, then it doesn't matter whether you have full containment or partial containment, hot or cold aisle, there will be bypass airflow. And I'll make that clear in just a moment. When we look at legacy cold aisle containment, the reason that this isn't as generally isn't as efficient is that the rest of the room becomes hot. We're fully containing the cold air in the cold aisle, and when you open the door to a room with cold aisle containment that's done very well, it may be 90, 100 degrees as soon as you open the door. And just a lot of people are not willing to live with that experience or work in that environment. And so while cold aisle containment is more popular because it's easier to deploy, it's often not done as well, meaning it's not fully optimized. The environment is not taken to the potential that it's capable of. And when we look at modular or partial cold aisle containment, I mentioned that there's that gap between the baffles in the top of the aisle. And this gap does not affect the potential for optimizing that balance between supply and demand air. And I'll point that out more clearly in the section that we talk about of bypass airflow. The benefits of modular partial containment is that it can be attached by staff, it can be relocated by staff, it doesn't require third-party installation or construction activities.
Thanks, Lars. So I'm going to just dovetail on some of the things Lars just said, and we'll talk about considerations around installation for both mechanically attached or kind of legacy containment as well as for modular. So legacy containment solutions oftentimes require skilled installation crews that may need to travel to the job site. Depending on the type and duration of the install, this could add up to a significant component of the overall project cost, but it's also sometimes unavoidable and absolutely necessary. With modular solutions, like you just heard from Lars, and like those offered by Upsite, and they utilize magnetic attachments, these can eliminate the need for a third-party installation, assuming you have the available staff, the skill level, and the time to do that self-install. If ROI is a necessary component for selecting a containment solution and your site conditions allow for the use of modular containment, then selecting a modular solution can offer a considerable cost savings and a much quicker ROI. Let's talk about a dynamic environment, right? So will your cabinets or aisles and containment design remain permanent for the foreseeable future, like it's a fixed design, and all you're going to be doing is moves, adds, and changes within the racks that are already permanently in place? Or are you going to need to plan for reconfiguration and layout changes as your demands change? So these types of kind of strategies for go forward into the future and how you might evolve into your room often dictate kind of or point you in a direction as to what options you might have from a containment methodology. My last point here would be that there's specialty situations that exist. We run into them seemingly more times now than not. Don't know the reason for that, but examples would be like a row that ends with a UPS or an RPP. So people might deploy power to all the cabinets on either side of the aisle through a row-ending UPS and RPP setup. So if you've got that kind of situation, this might not be conducive to modular or mechanical attachments due to the size and or equipment warranty issues. So there's absolutely ways we can accommodate these situations and are mostly treated as a one-off, and those almost always require some sort of site scoping visit and consultation with the end user or owner. So now we're going to talk a little bit about cooling optimization and why it's important. So these next two slides contain some key information, especially if you're an end user attending this presentation. So I feel these are probably two of the more important slides in this presentation. So we're first going to talk about what is cooling optimization. And not a huge fan of reading bullet points on a slide, but it's applicable here. So cooling optimization is indeed a process, right? It's a process of making adjustments to your cooling infrastructure to help you achieve your goals. And that process is iterative, right? Anybody that's attended like a quality control training, Six Sigma, that type of thing, you learn about making small incremental improvements. And that's exactly applicable to a containment methodology and how you need to manage these as an owner kind of post-containment install. So it's important that each time you do an airflow management improvement, that's also time to make the adjustments to your infrastructure to take advantage of what you just spent money on to employ. So let's go to the next slide. So why is it important, right? So implementing an airflow management solution doesn't make you efficient, just doesn't. I can't tell you how many times we walk away from a job and, all of a sudden the user's like, now what, right? So we try to consult with that to make sure they understand it's what you do as an owner or data center or facilities manager after you deploy the containment solution that makes you efficient. Airflow management and containment solutions enable you to take the next steps to achieve your efficiency goals, whether that be energy reduction, increased capacity in the same space, picking up some available redundancy or combinations of these. You look at that second bullet there, right? Without doing any of these steps after the containment, every airflow management improvement that's been made is just an expense. So a few examples that I'd like to share might be raising the set points of your crack or crawl units to more effectively produce the cold air required. That equals energy savings. And quite honestly, doing any of these changes post-containment, energy saving, for whatever the reason you're going about it, the energy savings usually does come along for the ride. But this could be a key step in what you do as an owner once the containment's implemented. And our industry's had our industry has tons of buzz phrases, right? But for a long time, there's been something out there that said that you could achieve energy efficiency upwards of about 4% for every 1 degree increase in set points, right? And that changes geographically and kind of site by site. But as a rule of thumb, that can be significant when you add it all up. Another example might be to use temperature monitoring to ensure correct temperatures that are delivered to the tops of your rack inlets. We had a client that was considering a fully capped aisle for cold aisle containment. We did the whole door thing. They used VFDs with their craw units, and they used an elaborate temperature monitoring solution, right? Temperature sensors at the tops of the inlets of all the racks in the cold aisle, tied back into the controls for some of the VFDs, and they dialed in that temperature that they wanted at the top of the rack. Lars mentioned the term bathtub effect a little earlier. It's exactly what this is, right? You flood that cold aisle with cold air, you get to the top of the rack, you see the temperature that you want, the VFDs kind of modulated at that point. There's also other customized options that are available, but the key with those is to consult with reputable vendors and partners that have a comprehensive offering and who understand airflow management. You don't need to do it alone. But stay away from those who just offer product or install services but can't give you the proper guidance and direction on how to achieve your goals. So now Lars is going to explain in some greater detail about how all of this works.
Thank you very much, Rob. Yeah, that's a lot of content in those couple of slides. Here's some images that might help you understand the concept of bypass airflow. It seems like a simple concept, but it's commonly misunderstood. So in the following images, we have a simple room with 1 cooling unit and 2 rows of cabinets. And these could represent, a large room with many cooling units and many rows of cabinets. The concepts, the ratios of the airflows all still apply. So in this room, we have a total of 10 units of air moving through the cooling units. That's generally referred to as CFM, cubic feet per minute. So we've got, say, 10 CFM, 10 units of air moving through all the cooling units. So if you add up all the air coming out of all the openings in the raised floor, it will be a total of 10. In this example, we have 2 units of air coming out of unsealed cable openings under 1 row and 2 units of air coming out of unsealed cable openings in the other row, and then 6 units of air coming out of supply tiles in the cold aisles for a total of 10. When you look at the rows and the IT equipment contained in those cabinets, each row, the IT equipment requires 2 units of air. So there's a total of 4 units of conditioned air required by the IT equipment. And this is a statement you don't hear very often, that the amount of air moving through the IT equipment is completely independent of the amount of air moving through the cooling units or moving through the room. You could turn off all the cooling units and there would still be 4 units of air moving through all the IT equipment. You could turn on an extra dozen cooling units and there still will be 4 units of air moving through the IT equipment. They have their own fans and those flow rates are independent. There's a few caveats to that when you get into the details, but that concept is generally true. So when the IT equipment is sucking up 4 units of air, but 6 are supplied to the cold aisle, then we have 2 units of air leaving the cold aisle as bypass airflow. So what do we need to do in this room? We need to fix, obviously, the bypass airflow coming out of the unsealed cable openings. And when we do that, we've now forced all the conditioned air to come out of openings in the cold aisle. And that's the way it should be. But we still have 6 units of bypass airflow because the IT equipment only requires a total of 4, leaving 6 units of conditioned air to leave the cold aisle. And this air will leave the cold aisle whether it has doors or a roof or baffles or not. This extra air will leave. If it's just baffles and a partial containment, then that 6 units will leave out the top of the aisle. If it's full containment with full doors and a full roof, then that extra 6 units of air that's not needed by the IT equipment is going to be forced through the IT equipment. Also wasted, same amount of waste. So this, though, does create the opportunity to optimize. We can now reduce the total amount of air moving through the room by either reducing fan speeds. It's better to run 10 cooling units at half speed than it is running 5 cooling units at full speed. There's greater energy savings by doing the 10 at half speed, by the way. So we can reduce the total amount of air moving through the room and now supply, say, 5 units of air into a cold aisle where 4 are needed. We've got 1 unit of extra air to maintain a little positive pressure and accommodate for some variations in flow rates through the IT equipment. So that's the concept of bypass airflow, and it's important to recognize the difference between the amount of air, the total amount of air moving through the room and the amount of air moving through the IT equipment. That's truly how you calculate bypass airflow, is take the volumetric flow rate through the room and subtract the amount of air moving through the IT equipment, and what's left over is bypass, regardless of anything else in the room. So I want to share one more concept with you, which is the 4 delta T's. Most people are aware of 2 of the delta T's in a computer room. On this image, they're labeled as 1 and 3. Obviously, we all know that air warms up as it flows through IT equipment, and we know that air cools down as it flows through cooling units. There's 2 more delta T's that are very important to measure, and they can really provide some insight as to the potential for optimizing the conditions in the room. And that's labeled as 2 and 4 on this image. And that's the change in temperature of the air from the time it leaves the IT equipment before it returns to a cooling unit, and the change in temperature of the air from the time it leaves a cooling unit before it gets to its warmest inlet temperature to IT equipment. This image shows an ideal scenario. We're not seeing much temperature change for 4 and 2, but in this image of typical conditions, we're seeing a lot of change. These temperatures, the colors are accurate to the color scale on the right. Very commonly, air is supplied from cooling units around 60 degrees, and yet the warmest intake to IT equipment is somewhere around 75 or 80. So why did the air warm up 20 or 30 degrees from the time it left a cooling unit? Well, obviously, some warm air mixed in from somewhere, indicating a need for improved airflow management. And when the air leaves IT equipment, we all know that it often leaves IT equipment at 100 degrees or more, but the return air temperature to cooling units is very, very rarely ever near that high. So why does the air cool off from 100 down to say 70? Why does the air drop 30 degrees? Why is there a delta T there in that location where there really shouldn't be any delta T? And that's obviously because conditioned air, extra bypass airflow from somewhere, either coming out of unsealed cable openings as indicated right there, or extra supply tiles somewhere else in the room flowing over the tops of the cabinets, extra conditioned air has mixed in and reduced those air temperatures. So measuring these other two delta T's, 2 and 4, the goal can be provide a lot of insight into how much room there is to optimize your facility. The goal is to get those other two uncommon delta T's to around 5 degrees Fahrenheit. Moving from 30 degrees potentially down to 5 degrees is the goal. Below 5 degrees, you kind of reach a point of diminishing returns. It's hard to achieve less than 5 degrees.
Good stuff, Lars. So while we've come up on the end of the presentation, I hope you all enjoyed the content and learned some things about row level airflow management, containment, and the science behind it. I think, I've been through and participated in a number of these, and sometimes the science explanations can go over a lot of people's heads, but kudos to Lars for bringing it down to where kind of some laymen and people who may not be as familiar with the science can really understand why this is all important. So here are some of the key takeaways from the presentation, some kind of nuggets. Again, with regard to just the row level airflow management, and it's not all about containment, right? There's a lot of areas in your data centers, in your rows, where you can start making these initial kind of low level investments. And these are all lower cost, kind of higher value investments that you'd make. So it's real important, just like at the rack level with the blanking panels and sealing off gaps between the side panels and the rails and all of those things. Same thing applies here with the row levels. When you need to get densities that are high enough where you need to kind of scale and you're going to go full-blown containment, hot or cold aisle, that's where you're going to do the actual containment projects. But rest assured that those kind of lower level investments need to be in place in order for a containment solution to be optimized and give you the ability to make the necessary changes. We learned a lot about the differences between modular containment and kind of some of the rigid mechanically attached stuff. Upsite's got a great offering for the modular, and I don't think enough people maybe consider that in their environments. But there's a lot of benefits that you saw, right? It can be reconfigurable. It can be self-installable, out of the box versus having to have an install crew. So some good nuggets for future thought there. So I'm going to hand it back to Isaac now, who's going to go through some of the questions that may have come in. Thank you all for your participation.
All right. Thank you, Rob. Thank you, Lars. We have quite a few questions coming in. Not a whole lot of time, but we are going to try to answer them as quickly as possible and try to get to all of them. If we, for some reason, are unable to get to all of the questions, we will follow up with you after the presentation to get those answered. So first of all, we had one that was actually asked through the chat asking, how is the adjustable mounting post attached to the raised floor, or is it attached to the raised floor support column?
So the way that that's mounted is holes are drilled through the raised floor tiles, and then bolts go through the plate at the bottom of the post, through the tiles, and then sections of unistrut are used to sandwich the stringers and the raised floor tiles to prevent it from tipping over, to make it a really secure installation.
Great.
I might echo too that in a lot of the projects we've done, whether it be with this post or without, that when you're attaching to a raised floor and you're using tech screws or some other type of hardware to attach, you think you're going into a tile and you're good there, but a lot of time, those tiles come out, they can lift. And there's a lot of momentum and kind of physics involved with how a door opens and closes. So that sandwiching it, using the unistrut or some other type of bracing under the stringers is really a best practice, and it's like a night and day difference from a rigidity standpoint.
Great, thanks, Rob. We also got a couple questions in regards to fire issues. We got one saying, regarding adding doors, how do you address potential fire code issues? How do you address this with the fire marshal? And conversely, we also have a couple questions in regards to a fully capped aisle and how that might be addressed with the fire marshal as well. Rob, do you want to take that one?
Yeah, so, it's important to understand how maybe rigidly enforced your local jurisdiction is with where your data center is located, right? So municipalities might have some rules that you need to be aware of. Your facility may have insurance requirements from your carrier that you may need to be aware of as well. So those are all important considerations, and the containment providers absolutely aware of that, right? So like for doors or a capped aisle, you don't want to prevent, or really in any scenario, you don't want to prevent the fire suppression from getting access into that aisle if that's where it needs to be, right? So if you've got overhead sprinkler systems, and I would say too that during like a scoping visit or whatnot, I mean, your installers or your vendor partners need to look at things like where the sprinkler heads are, where lighting may be. Sometimes lighting may have to be moved, especially if you're doing like hot aisle containment. You don't want things like, spanning in between, cutting your lights in half. But with regard to the fire suppression, like I said, with the capped aisle and the cold aisle containment, those products are rated, the UL listed and approved by Factory Mutual, which is one of the largest insurance providers, to be applicable for use and not impede the fire suppression from working in the aisle. But it is important. You need to understand what you got going on locally, and so do your trusted partners on the vendor side.
Great, thanks, Rob. We also got a few questions in regards to the presentation and recording, and the answer is yes. We will have the presentation slides and a recording sent out after the call here within the next day or two. All right, we've got another one here in regards to hot or cold aisle. What are the parameters for choosing between hot or cold aisle containment? Great question.
Rob, I'm happy to take that one. Sure. So it's mainly architectural. So if there isn't a drop ceiling and it's not, if there isn't a drop ceiling, then cold aisle containment is much easier to deploy. If there is a drop ceiling, there's a number of considerations, like, is it dirty? What's it going to take to clean it? Will it require an increase in the gaseous fire suppression system, an increase in volume, because you've now opened up that space and have to displace that air with a gaseous suppression discharge? So that's really the factor. If you don't have if you don't have a drop ceiling plenum for a return, then cold aisle is really what you're looking at. And you need to do a lot of work to provide education for everyone involved in the facility to understand that the room is now going to get hot, and we're containing the cold aisle, and the rest of the room is going to get hot, and that's a good thing.
I would add too that there are some challenges that come up, right? There's a lot of applications, a lot in colos and some on-prem data centers that don't have raised floors, right? They have slab floors. So what are we going to do there, right? So your perimeter air conditioning units are now ducted up above, and the returns are down below. And one of the keys here, we don't really talk about, I mean, you need to make sure you're providing a direct path of the return air back to these perimeters. So If you impede that, you're offering up a real challenge for yourself to manage that post-containment. So again, I talked earlier about aligning yourselves with quality partners who understand airflow management and how they can address these projects. And we've done capped aisles in slab floor environments for cold aisle containment. It's not a fun project, and it's not something modular that you can self-install, but it can be done, and it can be done properly, and you can make those necessary adjustments after it to realize your efficiency or capacity gains.
Yeah, and I'd add one more thing to that, listening to you, Rob, is that if you have a slab environment without containment, I guarantee it's very inefficient. Slab environments can be efficient, but they do require containment of some sort.
Great. Thank you, Lars. Thank you, Rob. And we got time for just one more question. And again, if we did not get to your question, I apologize. We will definitely follow up with you after the webinar to get those answered. So we'll go to the last question here. When using cold aisle containment, will there be wiring below the raised floor? Will the cold air be disrupted by that wiring?
Well, I would say the wiring, I'm assuming, is wiring for the infrastructure, for the IT infrastructure, whether that be power whips or communications cabling that may also be under the raised floor. So I'm going to fast forward a little bit. We're going to do one of these presentations specifically on the floor level, but that's a big deal, right? So especially in a legacy data center where people may have gone from their old thick blue mainframe cables and just lumped on the Ethernet cables on top. So that underfloor plenum is your main way of delivering, pressurizing that floor and delivering your cold air. So understanding where you may have impediments and how to remedy that on the front side before you go and put containment in is definitely going to be a best practice and something you need to be aware of. And so it may need an initiative where you got to pull out stranded cables and things that are causing obstructions. There may be other barriers under there that you can't deal with, like chilled water pipes that are in front of your crack units or things, or where air may be going where you don't need it to go. Do you have a lot of available white space or a knock area or office that's still on top of that raised floor that you don't need to pressurize a whole lot? So there's other things you can do with barriers under the raised floor to call it contain the under the raised floor before you apply the pressure into the cold aisle. And then really, we talked about this a little earlier, but understanding the IT load in the aisle, right? So what is the IT load in all the equipment in the 2 rows of racks on either side of the aisle? You need to be able to match that, that quantity of air with what you're delivering into that aisle. Because like Lars said, on the Delta Ts, those servers are going to pull that air whether you got a contained aisle or not. And if you have a contained aisle, then it's only going to pull the air from what you're providing to it. So if you got to be able to match it or exceed it a little bit. If you can't match it and you're underutilized there, you're going to have some big problems with some heats and some devices that aren't happy and start chirping a lot. So understanding about underfloor obstructions, making sure you can deliver the cold air that's required for that aisle. Those are all key considerations before you start putting in doors and capping the aisle.
Great. Thank you, Rob. Okay, so we're about 5 minutes over the hour here, so apologies for going a little bit over, and apologies for not getting to some of your questions, but like I said, we will follow up with you after the webinar to get those questions answered. Thank you all for attending this webinar. Rob and Lars, thank you for presenting. This really was a great presentation. Any closing thoughts by either of you?
Thank you, Isaac. Thank you for your time.
Yeah, and I just want to echo what you said at the beginning, and I hope, I appreciate everybody's time. It seems like, while we're all working from home and stuff, it's been a banner kind of 6 or 7 weeks for web presentations for everybody. So I appreciate you selecting ours, and I hope you all are safe and healthy, and, your family, friends, and coworkers as well. Have a great day, everybody.
Well said. Thank you all. Bye.